Yeah. So in chapter 3, so we are doing electricity, right? Um, right. So I will take over this, but you need to read first the first and second and third and fourth page. So you see in the fourth page there is a thing called representing electric circuits, and there are a bunch of symbols there, right? So you read quickly until that point, right? And then I will take over the entire lesson after that. Okay, so do it quickly now, guys. You hear me, right? Okay, now we have to understand. You can hear me, right? Guys, Ranjita, can you hear me? Yeah. So now we have to understand what is electricity. Okay. So this lesson is important in year 11. Yes, it is important, but typically year 11 we don't care, right? So in year 11 SACs we get these questions, but this is very much important when you are in grade 12, because in the grade 12 you have a lesson called power generation. In the power generation, typically we don't teach the basics of electricity, right? So this is the lesson we are going to do now, and then this will be dragged into there when you are in year 12, right? So I'll give you the basics here. Now think about this. If you have a battery, right? So if you have a battery here, this is plus node, this is minus node. Okay, this battery is connected to a bulb here. This is the symbol of the bulb, right? This symbol is not important, right? This is the bulb, right? Now there is a thing called current, right? There is a thing called current. Current is going from positive to negative, so current is I. Right? It's positive to negative, current is going. So what is current? That still we don't know. Right? So you say current everywhere, current is gone, current is there. But what is current? What? Okay, so this we have to understand. Now, there are two things here. This is inside the battery. This is outside of the circuit. Okay. Now, if you observe this one, you can see that outside of the battery, current flows from positive terminal to negative terminal. See, outside the battery, current is flowing from positive terminal to negative terminal. You might ask, like, why you are saying this? It's obvious, you can see that, but that is important. There is a lesson called magnetic field in year 12, right, which we'll be discussing like in a couple of months time. In magnetic field there is a thing called magnetic induction. So in magnetic induction this thing will come, okay, this concept will come, right? So that's what I'm saying. So outside the circuit, current flows from positive node to negative node. But if you think about the battery inside it is flowing from negative to positive. So that inside the battery, negative to positive, that concept is important. We will discuss that in when we are discussing magnetic fields. Okay. Now this is what is happening. Now, what is current? Okay. So what is current? Okay, what is current? Current is flow of electrons. Remember, current is flow of electrons. Okay, current is flow of electrons. So what is the definition of currents? Current is, definition is rate of change of electrons, rate of change of charges. Okay, so that means current is defined by Q divided by T. T means time, Q means charge. Okay, T is time, Q is charge here. Okay, so charge, I will discuss what is charge, right? Charge is measured by coulombs, right? C. Time is measured by seconds, right? So coulomb per second. Coulomb per second is what you have for current, right? So now typically, you know, current is measured by amperes, A. Amperes, A, right? So if you go to the shop, okay, 10 amperes, 100 amperes, 2 amperes, 3 amperes, 0.1 amperes, you will see those figures, right? So current is measured by amperes. Now the definition of the current would be rate of change of charge. So rate of change means, rate means always, you know, if you do math methods, rate means always respect to time, right? Rate means respect to time always, right? So in methods you will understand that most of you, or only Ranjita knows about it, that in differentiation there is a thing called DDT of Q. So I will discuss that in methods as well, because rate of change things are also coming in methods as well, right? There are few questions I met coming from electricity that I will discuss there, but that context is different to here, right? Here differentiation, any math is not going to be involved. So here amperes is A, and ampere has another unit, right? Coulomb per second. Coulomb per second. You know, Coulomb is a scientist, right? Coulomb is a scientist. Coulomb per second is another unit for ampere. So 1 ampere is equal to 1 coulomb per second, right? So we are talking about now flow of electrons, right? Now how do you measure it, right? Now practicals, this is how. Now think about, there is a timer, right? There is a timer, right? There is a timer. So then there is a circuit here, right? There is a circuit here, and we can measure the number of electrons passing through this one. Electrons are passing, right? Electrons are going through that one. So you measure the number of electrons, right? So N times E, right? N means number of electrons, remember that. number of electrons, and that would be Q here, right? Number of electrons. E means electron charge, charge of one electron, charge of one electron. Now, if you do chemistry, you know electrons, protons, right? You might have started chemistry. Electrons, protons, maybe yet in science, you know electrons, protons, right? So, electrons are negatively charged, right? So, charge Q is equal to Ne. So, now you will find the number of electrons which is passing through a time period, right? So, timer will give us the time period, right? So, suppose time period is T. Suppose the time period is T. So, current is divided by Q divided by T. So, Q is N E divided by T. Okay, N E divided by T. So, this is how we calculate that. So, you can say this number is in amperes, or you can say this number is in coulomb per second. Okay. Any questions? No. Now think about reality. Okay, in reality, if you have high temperature, this place has low temperature, right? High temperature to low temperature. So from high temperature to low temperature, heat is flowing. That means energy is flowing from high temperature to low temperature, right? Also, think about a water tank here, right? You have water here, right? So there is a small hole here, right? There is a pipe, there is a small tank here, right? There is a small tank here, right? So this is water. So water is flowing this direction. This is water flow. This is water. So this is happening, right? So now here what you have is high water pressure. High water pressure. Here you have low water pressure. So you will understand liquid flows from high pressure to low pressure. That's why the water tanks are on top of your roof, right? So on top of the roof, high pressure, then when it comes down, it's low pressure. So high pressure to low pressure, water flows. So in reality, in practice, high to low, the things are flowing. High to low. Now we will go into electricity. Now suppose there is a wire here. Right? So this is a wire. Now current is flowing this direction. Forget about current. Electrons are flowing in these directions. Electrons. right? Electrons are flowing in this direction. So if electrons are flowing in this direction, something here should be high. Something here should be low. Something here is high, something here is low. What is that something? Right? Understand the story. This something is nothing but electric energy. So like in the first example, see, in the first example, temperature high, temperature low, right? High temperature to low temperature, heat is flowing. Now you understand, when you have high temperature here, you have high energy here, right? Here you have low energy, right? Right? So high energy to low energy, the heat is flowing, right? So high energy to low energy. So energy is measured by temperature there. So we say high temperature to low temperature. Now when it comes to here, high electric energy to low electric energy, electrons are flowing, right? Any questions? No. Okay. Now think about a battery. Think about a cell. Cell is another word for battery, right? If you do chemistry, in unit 3 chemistry, there is a dedicated chapter for galvanic cells, Daniell cells, right? Different cells, right? Think about a cell. Cell is a battery. So in a battery, you have a negative terminal, we call it negative terminal, and a positive terminal. Battery is like that, right? So this is positive. This is negative here. Okay. Now, when you take a battery, you will see this negative and positive. What do you mean by that? This negative means electric energy, right? So more electrons in this terminal. Okay. Here positive means not more protons. Positive means less electrons. Less electron is positive in this description, right? So less electrons in the positive terminal. Okay. So now understand, I'm going to connect a wire. Right? I'm going to connect a wire now. So now what will happen? So more electrons, less electrons. What will happen? Electrons are flowing from more electrons to less electrons, right? So electrons are flowing this way. Electron flow. You understand why electron flow is going from there? Why? Because here more electrons, right? So many electrons are there. Here less electrons, right? So more electron to less electron, the flow is happening. That is the reality. Yeah. Okay. That is all good. But this is the electron flow. Electron flow, we call it outside the circuit. Yeah, electron flow outside the circuit now. Then, physicists, they wanted to have a definition for rate of change of charge, right? Q divided by T. So they define the current, right? So actually people say, oh, current, right? So we have current in our house, but nobody can feel the current. Nobody can see the current. We can feel in an electric shock, not the current, but the electrons. Electrons, a lot of electrons are coming into your body, not the current. Current is a junk name given by us, right? So we define current to be other way around. This is current, I flow, current flow. So what I want to tell you, by definition, this is not my definition, this is a universal definition. By definition, current okay, let's see, current I flow and electron flow are opposed to each other. So if the current flow is this, on the same wire, electron flow is this way. Right? So this is what we know now. Now, summary of what I said. You have a battery, right? Connected. This is positive, this is negative. Electrons are going this way. Electrons. Now you have a battery, positive and negative. Current is going other way around, right? So the how do you represent a battery in this way? This is the notation. So this one is the positive, the longest line would be the positive. This is going to be negative. This is going to be positive here. This is going to be negative here. Okay. Okay. You got to know what I'm saying? But this is what we use. We use this picture always. Okay. We are not considering the electron flow but the current flow. So by definition, current flow is opposite to the electron flow. Actually what is flowing is electrons. There is nothing called current. Current is something hypothetical quantity, right? We use for our understanding purpose. Okay. Any question? Any question? No. Okay. Now, next one, again very important, energy inside a battery. Inside a cell. In chemistry also you will understand, but in chemical perspective you will understand this. Okay. So energy inside the cell. Now we'll think about this again logically. Right. Or this is the notation. So this is minus node, plus node. Plus node here, minus node here, right? So this is what you have here. Now here you have a lot of electrons. A lot of electrons. Here lesser number of electrons, right? So when you have lot of electrons, you have energy, right? Energy. A lot of energy. Here you have less energy, right? So on those terminals, high energy, low energy, right? Now if you think about this as a unit, right? If you think about this as a unit, there is an energy difference inside. Okay, very important to understand. There is a energy difference inside the battery. Okay, we call it delta E. Delta we call it. Delta means delta is used to denote the difference as well, right? Right? Delta, if you did math with me, you know delta has two meanings. One is difference. The other one is small. Depends on the context. You can, if you write delta E, if you don't know the context, then you can think, oh, this is small energy. If you know the context, right, then you will refer to difference in energy. So here we have difference in energy. So remember delta. In math methods also you have that in differentiation. Delta part. We will discuss that in the method class. So yeah, there is an energy difference as this. Okay, so sometimes people use delta E, sometimes people use E, sometimes people use a weird notation like we call it epsilon. We call it epsilon, right? That's a Greek letter, epsilon. So if you see this in front of a battery, that means energy difference, energy of a battery. So this is nothing but energy difference inside the battery. So this is energy. This is energy of a battery, we call it. Okay. Energy. This is energy of a battery. Okay, all good. This energy is called EMF as well. EMF. This energy is called EMF. You will see EMF, E, delta E, energy of a battery, right? In chemistry also you will see EMF. So that you have to understand, we are talking about the energy inside a battery or energy of a battery. What is EMF now, right? EMF means electromotive force. EMF means electromotive force. Okay. Yeah. That's pretty good. Any questions so far? No? All good? Tanuri, you all good? I can't see you.
Yeah, okay.
Okay, so we understood what is a battery. Battery is a cell. Inside the cell there is a energy. That energy is actually resides inside as energy difference. Why energy difference is happening? Because there are two terminals, minus terminal and positive terminal. Minus terminal means at the minus terminal there are so many electrons. In the positive terminal there are less electrons. So there is an energy difference inside the battery. That energy difference is called the energy of a battery, and that is called EMF, which is electromotive force. That is the story. Okay, so it's not a big deal. Okay. Now, what is the relation? This part is very important, guys. Okay, what is the relation between this, which is EMF, okay, EMF, and I current? What is the relation between E and I? Right? What is the relation between E and I? This we have to understand. Now we have to understand one thing here. Consciousness is very important. E means energy source, right? This is energy. What is this one over here? Current. Current means, by definition, that is Q divided by T. Q means number of electrons. Electron flow within a time frame. That is the definition of the current. This current term is a man-made term. Okay. Now the current is not energy, right? Current is just electron flow, right? Amperes, right? Amperes. It's a different thing. Energy is energy, joules, right? Energy is energy, joules. Now, how do we understand the relation between this? So, why we need to talk about the relation? Why we need this relation? The reason is this. If you have a battery like that, right, and this is connected with a wire, this is positive, this is negative, right? E is here, right? Suppose E is 10 joules, right? So, joules, or we call it volt, V, or V, which is called volt. Okay, so the volt is another unit for energy, right? 10 volts. You get a AA battery. You will see 0.5 volt, 1 volt, 2 volt, 3 volt, like that, right? 5 volt, like that. So this energy is 10 volts. So what is the meaning of this energy? Energy inside the battery, right? Energy inside the battery. So now we know that current is flowing from positive node. See, current is flowing from positive node to negative node, like this. Current. What about the electrons then? Electrons is other way around, right? So don't worry about the electrons, because all the time we are dealing with the currents, right? Electrons are always opposing to the direction of the current. So current is from positive node to negative node, like that, right? Now, there are two things here, right? One is energy, right? The other thing is this current, right? So now how do we understand this? So the current is flowing now, right? So this is the best way to understand. Think about this. Think about this. This is energy, right? So I'm going to refer this current to be a cart. I'm going to refer current to be a empty cart, right? Now empty cart starts from the battery, right? So that means what this cart is doing, cart is going to load the energy E. So E is inside the cart, right? Then when the current is flowing, current means the cart is flowing, cart is traveling with that energy loaded, right, throughout the circuit, right, throughout the circuit. You understand what I'm saying? Current is the cart is going to load energy from the battery and travel around the circuit. This is what current is doing. Okay, next story. So I'm taking this story so that you will understand the things better. Okay, otherwise I don't want to go into these childish kind of examples, right? But this helps enormously. Now suppose I'm going to change this a little bit. Here you have a battery here and you have a bulb here. This is a bulb. You have a battery. Suppose battery has 5 volts, right? Battery has 5 volts. Then current is going this way, right? We know that. Now when you have a circuit like this, you know the bulb is lighting, yeah? Right? So bulb is lighting means what? Your bulb, your room, the bulb in your room is lighting. What do you mean by that? That means energy is going out, right? Energy is going out. So this is how you understand this. Now I told you I is the cart, right? I is the cart with 5 volts there. Right? 5 volts there. Now what this cart is doing, this cart is a very reasonable guy. This cart is a very reasonable guy. When he is going to see a obstacle, right? Obstacle means bulb. Bulb means a resistor. Right? So what is a resistor? Resistor means barrier to flow current. Okay, so it's a barrier to flow current, right? So the cart is coming to the bulb. So the cart is a very sensible guy. So the cart sees that, okay, there is a resistor there, which is a bulb. So what that cart is doing, cart is going to unload all the energy what it has. 5 volt is going to be unloaded. Then cart is empty here, so the empty cart goes here now. This is what is happening. Then cart again goes to inside the battery, again load 5 volts, come back to the bulb, again release that energy, again go back to the other node, then again load, unload, load, unload, load, unload. So that's why continuously you see bulb is lighting. Why? Because loading, unloading, loading, unloading, loading, unloading is happening continuously, very fast, right? So I took this example, cart example, so that you will understand better. Otherwise, if I tell you in science way, a little hard, right? Why we suffer, right? Yeah. Okay. So this is what is happening. So I told you this cart has sense, right? He's very sensitive, right? Like like, how do I explain this? You know, like dogs, like dogs, you know, like the trained dogs, like, you know, the police dogs, you know, like when they can smell some drugs, like even though like far away, yeah. So these are very, they can sense this like a dog, right? So this cart can sense. What this cart is sensing is the cart can sense the number of barriers ahead. Cart can sense, oh, I have one barrier ahead. Cart can sense, oh, I have two barriers ahead. Cart can sense, oh, I have three barriers, but three different barriers ahead. So likewise, cart can sense the number of barriers. For example, okay, okay. For example, suppose you have a bulb here. I would say resistor is 1 ohm, right? Resistor is measured by ohms, right? Barrier for current flow. This is measured by. These are new languages, right? This is measured by ohms. OHMS. Ohm. Right? Ohm. Ohm is a. OHM is a scientist. Right? Ohm is a scientist. So resistance is measured by ohms, right? So the symbol would be this kind of a weird symbol like that. All are Greek symbols, okay? Ohm. There is another resistor. R 1 ohm. Equal resistors. That means equal bulbs, right? You can think in that language. Okay? So suppose this is A and this is B and this is C here. Okay, ABC. Now the question is, first one, what is the energy drop? What is the energy drop between AB and BC? In other words, in technical words, I'm giving you technical words because they are coming in the exam. Technical words. What is the potential difference what is the potential difference between AB and BC? Okay. Yeah. So now how do you understand that? Now you will understand here, right? So I'm not going to draw the cards, but you will see the card is coming with 5. Card can sense, I told you, card can sense here, when it is here, card can sense there are 2 equal resistors, see? So what card is doing, this. Cart is the current, right? 5 is coming. Then when the cart is going to leave 2.5 joules or volts here. Then when the cart is here, inside the cart you have 2.5. Then the cart is empty here, right? Empty cart goes here. Then again a new cart with 5 volt loaded is coming there, right? So there would be a 2.5 volt. Energy difference, right? So that's why I told you cart has a sense. He's a very reasonable guy. He's going to divide equally. right? So we call it potential drop between A and B. We call it, how do you write it technically? Potential is potential or energy. Potential means energy, okay? Potential or energy is measured, is denoted by typically capital P, capital V, capital P, capital E. You can use anything, right? So potential between A and B is now 0.5 volt. Potential B and C would be 2.5 volts. So now what is potential? Potential means nothing but energy. Energy between A and B is 2.5. Energy between B and C is 2.5. Make sense? Understand the story. Like, otherwise this is going to be very hard to understand. This story helps enormously. Have you done these things when you were in year 10? Do you know these things? Ruchira, do you know these things? You don't know Ohm's law, you don't know? Okay. Okay. That's fine. Because I remember I learned this when I was in grade 9 and 10. 9, maybe 9, 10. These things I learned. But depends, right? Depends on the curriculum. Now anyhow, so this is happening, right? So now what is the next question you should be asking? What is the next question you should be asking? As math students ask that question. Yeah. What is the next question you should be asking? Guys, be in the story. There is a tiger in the story. There is a rabbit in the story. Very close to each other. I'm asking, what is going to happen? You can't stare at it. You have to say, okay, maybe tiger is going to kill rabbit. Or maybe rabbit is going to kill tiger. Or maybe they are going to escape. Something you have to come up with, right? You have to be in the story. So the next question should be, if you are keen into the story what I am telling, now I told you here, when you have 1 ohm here and 1 ohm, they are equal, right? They are equal. When they are equal, they are equally distributing. See, 2.5 to 2.5. Equally, they are going to distribute this. Okay. You got what I'm saying? They're going to equally distribute it. Now the next question is, if these two are different, in your house, your room has a different bulb, in the living area you have a different bulb. So the resistors are different. So the energy output would be different, right? These two are different. So if that happens, what is going to get, right? Okay, now discuss that one. I will give you some hard questions later, but once after you learn the strategies and the story properly. Yeah. So suppose you have energy 12 volts here. Okay, plus and minus here. No, I forgot to draw this one. Where is the resistor here? Resistor, barrier to flow current. Yeah, This is measured by ohms, yeah, that's true. Symbol would be something like wiggly thing like this. This is the symbol for resistor. Okay, so this is a resistor. Now we call it R is equal to 1 ohm. This is R is equal to 3 ohms. Okay, so this is A here, this is B here, this is C here. Right. My question is, find the potential difference between AB and BC. Okay, do that. Try to do this question, everyone. Quick. So I'll give you the answers here.